In this video, we're going to continue on particle dynamics and free body diagrams. We'll do example 40 on the lecture notes. So the problem is we have a ball, noted as point P, and it's supported by a string. And the ball is moving in a horizontal circle with a radius of 2.5 meters and at a speed of 10 meters per second. So we know the velocity equal to 10 meters per second. We know the radius, and we're given the gravity is pointing downwards. And the question is, we need to find the angle phi. So where do we start with this problem? If we just look at this problem intuitively, what is going to give our angle phi? So the question is, how does phi changes the motion of the ball? So when we talk about the motion of a particle, we have to associate it now with the force. So what are the forces that we have on this ball? First, as we covered last time, we have the string force. And second, we'll have the gravity force, which is the weight of the ball. So let's decompose and draw a free body diagram for this object. So we have, if we're looking from the side, okay, we're looking at the side view of this figure. And this is the wall. And this is the plane that the ball is moving. So that this represents a circle if we look from the side. So we have the point P here, and the radius R. And we know the gravity force is pointing downwards. So the type of forces that we will expect on this ball, we have gravity, which is weight, and we have a string force, let's call that tension, T. Okay. So if we're to draw a free body diagram, which we eliminate all the other components, so we get the particle P, or the ball P, with the weight pointing downwards, and the tension, which makes the angle of phi with respect to the local vertical. So this is how the phi is going to change our motion. Depending on the angle of phi, we're going to get a different component of the tension in the horizontal plane. But we'll see that in a moment. But to solve this problem, we have to start by finding the acceleration of this ball. We know by Newton's second law, we know the sum of the forces is equal to mass times acceleration. In order to find the tension or the forces on the particle, we need to solve for the acceleration first. And recall that Newton's second law only works in an inertial frame. So we need to find the acceleration of the ball or the particle P in the inertial frame. So the question becomes, find the acceleration of the particle in the inertial frame, and let's use E as the inertial frame. So what is the acceleration of this particle in the inertial frame? Let's go back to the problem. We have the particle moving in a horizontal circle with a radius of r equal to 2.5 meters. So without looking anything else, let's just look at the motion of this particle, and it's moving in a horizontal circle. If we were to look down into the motion of the particle, we see a circle, and we have the particle P on the circle moving at a velocity of v. And we know that radius is r. So at this point, we have converted the problem from a dynamic problem to a kinematics problem, where we just want to solve for the acceleration of the particle in the inertial frame. This is a typo. Problem 2a, kinematics problem. Okay, so let's mark the inertial frame as E1, E2, and E3. And we have a rotating frame that's rotating with the particle. Now we're going back to the simplest type of kinematics, a planar rotation with just one rotation. So to find the acceleration of point P in E, we take the derivative of the velocity of point P in E. And without going through the position vectors, and the problem already give us the magnitude of the velocity. And if we have the frame, A frame, rotating with the point, then we know the velocity of point P in E is simply the magnitude times the direction, which is A2. I recall that when for circular motion, we know the velocity is always perpendicular or tangent to the circle. And if we have A1 direction pointing always towards the point, then we know the A2 direction is perpendicular, which is along the velocity direction. Okay, now we replace the expression for velocity of P in E with V times A2. Now we can use basic kinematic equations to solve this equation. So again, just as a reminder, in the kinematic equation, now the question becomes, how do we find the angular velocity of A in E? If you remember, for a circular motion, the velocity is equal to the angular velocity of the rotation times the radius. Okay, this is only true for a circular motion. Then we have the angular rate equal to V over R. See, it's just solving for omega in terms of V and R. Now, what's the angular velocity in the original equation? We have the angular velocity of A in E is equal to the magnitude times the direction, which is A3 or E3. So we get the acceleration of point P in E equal to, so what's the derivative of VA2 hat? Okay, so what's the derivative of V? We know for a circular motion, the velocity is constant, and this is given without stating that V dot equal to 0 motion. So we have V dot equal to 0. So the acceleration of point P in E is simply omega A3 cross V A2. We can substitute omega with V over R. Then we get negative V squared over R A1. So this is the acceleration of the ball P in the E frame. Okay, and E is the inertial frame. So essentially we have solved the acceleration of P in the inertial frame. Notice that although it is expressed in the A1 frame, remember that no matter which vector basis we use to express a vector, as long as we're solving the acceleration of velocity in the inertial frame, we can express the same vector in different reference frames. So this is okay. And just looking at the equation, we know A1 is always pointing inwards to the center from the point P. And V squared over R, that's acceleration due to circular motions. The next step then is to apply Newton's second law to calculate the forces. Okay, now we have found the acceleration of point P in the inertial frame, which you can just simplify as m times a hat. And we get the sum of the forces is equal to mass times negative V squared over R in the A1 direction. Okay, we know from earlier the free body diagram that the sum of the forces is equal to W bar plus T bar. And let's express W bar and T bar separately so that we can get an expression for the sum of the forces. So W bar has a magnitude of mg. So it's mass times gravity acceleration, and it has a direction of g hat. And what is that g hat? If we go back, we know g hat is pointing downwards. When we drew the reference frames here, we are looking from the top. So G is pointing into the paper, whereas we have A3 and E3 defined as pointing out of the paper. G hat has the negative direction of A3 and also equal to E3. So that we get W is equal to negative mg A3 or negative mg E3. Now what about the tension force? Again, let's go back to the original plot. We know this string is rotating with the point. So the tension force will also have component in the rotating frames. So the most reasonable reference frame for us to use to represent the tension force is the rotating A-frame. So we have the structure and the string has the point P attached, and it makes an angle of phi. So if we always put our view as perpendicular to the r vector, so essentially we are following the movement of the particle no matter where it goes. And we'll see this geometry for the string. so that we know this is always the A1 direction, and this will be the A3 direction, and A2 will be into the paper. Now we can start resolving the tension forces in the A1, A2, A3 frame. So let's again draw a cleaner diagram. We have the tension force, and let's move the reference frames so that we can better represent the vectors here. And we know this angle, that's phi. So the tension T has a magnitude of T times cosine the angle between A1 and T in the A1 direction, and plus the magnitude of sine. Let's use cosine phi in the A3 direction. And we know cosine pi over 2 plus phi is equal to negative sine phi. So essentially we have solved for the tension T in the A frame. And let's find the sum of the forces and use Newton's second law. Again, let's look at the acceleration. A bar. We know the A bar is expressed in the A frame. And we have the sum of the forces. It has two components, W bar and T bar. And we have W bar expressed in both A frame and E frame. And we have T bar expressed in the A frame. So logically, we'll choose the A frame to represent all the vectors we have for Newton's second law. Let's just write W bar plus T bar is equal to mass times acceleration. Negative. Just replacing what we have solved for each variable. Negative mv squared over r a1. Then let's resolve the vector additions in different components. You have t cosine 5 minus mg in the A3 direction. And similarly, we'll have, and that is equal to 0. When we say the vector is equal to 0, that's equivalent of saying two things. The components are 0. This is equal to 0, and mv squared over r minus t sine phi equal to 0. So what do we do next? We know from the equation that m is a constant, that's the mass of the ball. G is a constant, that's gravity acceleration. We know v is already given, that's a constant. And r, that's a constant. M is a constant. So the only two variables we have are the tension and an angle. Thus we have to solve for the tension and the angle, but the problem only asks for the angle phi. So we can replace the t in the second equation using the first one. So from the first equation we get t is equal to, and let's substitute that in the second equation, we will get mass v squared over r minus mg cosine phi times sine phi equal to 0. And let's take the common term out. We have m v squared over r minus g times sine phi over cosine phi. And we know sine phi and over cosine phi, that is tangent phi. So in order for this equation to be 0, we know tangent phi is equal to v squared over g r. Of course, then you can plug in the numbers. V equal to 10 meters per second. If we assume g is equal to 10 meters per second, although it's sometimes 9.8, just to make the calculation a little bit easier. And r is equal to 2.5 meters. You can get a value for the angle. So let me summarize the procedures that we use to solve a dynamic problem using Newton's second law. So a systematic procedure for applying Newton's second law. So first, we need to obtain the inertial acceleration, because we know Newton's second law only applies for an inertial frame. And in static problems, we have a bar equal to 0 because nothing is moving. Second, we need to model all the forces on the body, whereas we need to draw a free body diagram to represent all the forces. And 3, if necessary, you'll have to introduce a set of basis vectors and resolve the accelerations and all the forces into component relative to that basis vector. So in the example that we just did, we have used the rotating frames. And number 4, apply the force, the sum of the forces equal to mass times the acceleration to get scalar equations. And the rest is just solving for the scalar equations if you need to.